So, last class we looked at some of the applications of Grubler's criterion and number synthesis, basically determining the numbers and types of links you would need for say a single degree of freedom linkage would mean that you would have to, for mobility equal to 1, you have n should be even, I max which is the maximum order link would be n by 2, the order of the maximum number of nodes in a link can be n by 2, and then you have to satisfy minimum of binary links greater than or equal to 4, and then you have to basically satisfy the equations n2 plus whatever ni equal to the total number of links. And from the mobility criterion we saw that you have n2 equal to 4 plus sigma p equal to 4 to I p minus 4 np, because this we obtained from the mobility criterion. So, if they satisfy these two equations, then they give you possible solutions for the number synthesis. Okay. So, satisfy p minus 3 np. Okay. So, for say n equal to 8, you would have n2 plus, okay, you only have I equal to 4. So, n2 plus n3 plus n4 will be equal to 8, and then you will have n2 equal to 4 plus n4. Okay. So, as long as these are satisfied, you have your possibilities could be n2, n3, n4. So, you could have 4 and 4, or you could have 5, 2, 1, etc. So, you can, because these all satisfy these equations simultaneously. Okay. So, that is your number synthesis. Then we moved on to looking at inversions and the Grashof's criterion. So, if S plus L, the shortest plus the longest link, is less than P plus Q, then you have the Grashof or the Grashof type 1 linkage, where if the link next to the shortest link is fixed, then you get a crank rocker. So, if 4 is the shortest link in this one, you have 1 or 3 fixed, here 1 is fixed, you get a crank rocker. If the shortest link itself is fixed, you get the double crank, or also called the drag link mechanism. So, these two are called non-distinct inversions, link next to shortest link. And in this case, the link opposite the shortest link is fixed. So, you are only concerned with the shortest link and its location with respect to the fixed link to determine the kind of motion that you have. In the case of the Grashof double rocker, the coupler, which is the shortest link, makes the complete revolution. So, it functions like a crank, and I showed you these animations, I will not do it again. Okay. So, in the Grashof type 2, which is S plus L is greater than P plus Q, all 4 inversions function as double rockers, or actually correctly speaking we call them triple rockers, because all three links can only rock between limits. There is no link that can make a complete revolution. So, they are typically denoted as RRR. Okay, you have no C in the notation. So, that is the Grashof triple rocker. Example, there is nothing wrong with being a Grashof triple rocker, it depends on the application. There are plenty of applications where you do not need a link to make a complete revolution. Okay. So, it is perfectly, it really depends on the application as to whether you need a Grashof or a non-Grashof linkage will do. Okay. Now, the special case is when S plus L equal to P plus Q. And some of the a couple of special linkages are called the parallelogram or kite form of these linkages. So, obviously, if you have a parallelogram, then S plus L equals P plus Q, and you will find many applications of the parallelogram form of linkage. So, here you will see that the input and the output motions are the same in the parallelogram form, and you will see that the coupler is essentially just translating in the plane. Okay. So, the orientation of the coupler does not change at all. So, you will find many applications where this is very useful, and it is also very useful when you want to basically reproduce the input motion at another point. So, the parallelogram mechanism is very useful for that. One of the problems with the parallelogram mechanism, which you do not see in this particular simulation, but you will see in the so this form here, the second one. So, this is the parallelogram form, and this one where it is crossed like this is called the anti-parallelogram form. So, it is the same links in the anti-parallelogram form. So, you can see here when the links line up like that, okay, that is called a change point, and there is some unpredictability associated with that change point. So, you started off with an anti-parallelogram mechanism, okay. You can see here it switched to a parallelogram mechanism. So, your output becomes unpredictable. In this case we did not see this because the inertia of the links, if the inertia of the links are able to carry it through, then you do not have a problem. So, here I think the yellow link, the mass of it is enough to sort of carry it through and not have it switch to the anti-parallelogram form, but otherwise that is a real possibility. So, when it goes through a change point, the motion becomes unpredictable, and so parallelogram mechanisms can be troublesome if you are using them over the entire range of motion. So, one way to deal with that, there are a couple of ways of dealing with that. One is you put another parallelogram mechanism that is out of phase with this, so that when one is at the change point, the other one is not, so it drives it in the direction that you want. Okay. The other thing is, do not run it over the entire range. If you may not need to run every mechanism over the entire range of motion. So, if you need the parallelogram action only for a certain, in say a rocker fashion, you are perfectly justified in using that between those limits. You do not have to necessarily run it through the entire, you will still get the duplication of the input motion in the output motion. It all depends on the application that you need. The other form is the kite form, where you have the two short links. So, it is like this. So, it could be like this or the other way. So, that is called the kite form, it looks like a kite. And here you have the input motion, the speed of the output motion will be half that of the input motion. Okay. You can see that here. Okay. So, these are the Grashof neutral mechanisms. Similarly, for a slider crank, you could again have 4 inversions, where you have the side adjacent to the and you can see, I will show you the possible inversions. So, here you can see that all 4 of them are essentially the same slider crank, but in each of these a different link will be fixed. So, let us start with basically the path is fixed and the slider block is moving back and forth on that path. So, the slider block has translatory motion in this case. Then here you see that the slider block has more complex motion. Okay. So, here the shortest link is fixed, then in this case this link is fixed, the link to which the slider block pivots. So, the slider block can only pivot about that point, okay, and the other link moves with respect to that. Fourth case, the slider block itself is fixed, which is similar to kind of the path being fixed. So, that so these are the 4 inversions of the slider crank or the 3R1P mechanism. So, a Scotch yoke is a mechanism which has 2 revolute and 2 prismatic joints. So, if I have link 1, 2, 3 and 4, the joint between 1 and 2, sorry, this should be R1, R1, this is a between 2 and 3 is a prismatic joint, no, where is, okay, this is 2 and 3, so that is R2, that is the second revolute. Between 3 and 4 is your prismatic joint, and between 1 and 4. So, this is the kinematic chain. You have 2 prismatic and 2 revolute joints, and then depending on which link I fix in the kinematic chain, I can get. So, here link 1 is fixed and I get a Scotch yoke. Okay. So, if I fix link 2, okay, then I get what is known as an Oldham coupling. Okay. So, you see between 1 and 2 is a revolute. So, the link 2 is not shown, which is fixed, the bearings are, so that is your link 2. Between 2 and 3 is also, so between 2 and 3 is a revolute joint, and between 1 and 2. So, basically for misaligned shafts you can use a coupling like this, which is essentially a kinematic inversion of the Scotch yoke. So, you have 3 and 4, you can see that this link you have translational motion and then orthogonal translation motion between these two links 1 and 4. Okay. So, this is not a planar mechanism. This is not a planar mechanism, but it is an example of the 2R 2P mechanism. So, it is typically used for coupling misaligned to take up misalignments in shafts, so that the rotation of 3 is transmitted to the rotation of 1 or vice versa. Okay. So, in this case you have, in this inversion you have link 3, no, which link is fixed here? Link 2, 3, 4, 4 is fixed, link 4 is fixed here in this inversion, link 4 is fixed. So, between 4 and 3 is a prismatic joint, okay, and then between 2 and 3 is a revolute, between 1 and 2 is again a revolute joint. So, this is called an elliptic trammel, and you can see that this point traces an ellipse. It is called an elliptic trammel. If you fix 3, it will be similar to the 1 fixed. So, it will just be a non-distinct inversion of that. Okay. So, this is how. So, relative motions of the links remain unchanged, but overall when you look at it with respect to the fixed link, what you get is, or your fixed coordinate system, you get different motions in the plane, different output motions. Let us also look at the 6 bar chains that we have seen, the 2 chains. So, what are the 2 chains? The Watts and the Stephenson. So, if I look at the chain, remember the Watts has the 2 ternary links directly connected to each other. That is your Watts chain. Then the Stephenson's chain, you have the 2 ternary links separated by a binary link. Okay. So, again you have, so this is the Stephenson's chain. In the case of the Watts mechanism or the Watts chain, if I fix ternary link 1 or 4, okay. Say I fix 1, what do I get? I get 1 4 bar chain driving another 4 bar chain, okay. So, if I take this 2 as my input, 4 will be the output for the first 4 bar chain, which will be the input to this 4 bar chain 1 4 5 6, okay. So, that is, and whether it is 1 or 4, basically they are non-distinct inversions in terms of the form of the inversion, and that is called a type 1 Watt mechanism. Watt's mechanism. So, these are two 4Rs connected in series. Where input of the second is the output of the first. If I fix any of the binary links, so this is okay, the other 4 binary links, if you look at the form, it is pretty symmetrical. So, if I fix any of the binary links, what do I get? Say I fix link 2. If I look at this closed chain, right, it is essentially a 4 bar, 1, 4, 3, but with additional coupler links. Okay. So, I have 4, 5, 6, 3 coupler links in the mechanism. So, I can get more complex motions in the plane, but essentially if I just look at input and output, it is essentially just a 4 bar. Okay. So, unless I am interested in that complex output motion of the coupler, if I can use a 4 bar for this application, I should use a 4 bar, okay, because it does not really give me anything else if I am just looking at 3 and 1 as my output and input links. Okay. And it does not matter which of the binary links I fixed, I get a similar configuration. So, if any of the binary links, namely 2, 3, 5, 6 are fixed, the input and output relationship, if I just look at the links that are pivoted to the ground, is identical to that of a 4 bar. But it has 3 floating links, but the 3 floating links can provide more complex motions in the plane. I should not say the 3 because 4 will do what a 4 bar does, 5 and 6, but the 2 additional floating links. Floating links can provide more complex motions in the plane. Okay. So, those are, so if you look at distinct inversions with the Watt's chain, you are basically getting 2 different types, 2 distinct inversions. One is if you fix the ternary link, one is if you fix one of the binary links. Actual motions of course will be quite different depending on which link you fix, because that will be dependent on the dimensions of the links. Now, let us look at the Stephenson's chain. I could fix one of the ternary links. Let us see if we get something different. Okay. So, inversions of the Stephenson's chain. You actually have 3 different kinds of inversions you could get. So, let us say type 1. One of the ternary links is fixed. Okay. Type 2, one of the binary links that are connected to each other. Fix one of the binary links connected to each other, which would be which ones? So, say I call 1, 2, 3, 4, 5, 6. This would be fixing 2 or 3. This is fix 1 or 4. And then the type 3 inversion is fix one of the binary links connected to the ternary link, connecting the ternary links, sorry. That is fix 5 or 6. If you fix 6, for instance, you are essentially getting a 4 bar again, similar to the Watt type 2 is what you will get with this. I will get some simulations for these and show you, okay, for these, because these motions are more complex than in the case of the Watt chain. So, these are inversions. The concept of inversions we will use quite extensively when we come to synthesis, because inversions in a kinematic chain, the relative motion between the links is the same. So, we will use that concept repeatedly when we do synthesis of linkages. So, it is a very important concept for you to remember. Okay. So, in many cases, if you remember, we said we could when we did the mobility or the type synthesis, we made this assumption that any linkage can be represented as a pin jointed linkage, right. It can be represented as links connected by simple hinge joints. So, here is how the slider crank, the reason we focus a lot on the 4 bar is it turns out that many linkages can be represented as 4 bars at least instantaneously. Okay. So, in many cases you can make a kinematic representation of a link, say with higher pairs or with other kinds of joints, as a 4 bar for analysis. And therefore, so if you for instance, if you take this 4 bar, essentially if you look at the motion of this point, right, this link 4 is pivoted to the ground at R4. So, this traces an arc. Okay. So, this may be represented as a block with that curvature moving on that curved surface, but this is not really considered a prismatic pair. Okay. Because essentially because of this radius of curvature, it has a finite radius of curvature. So, this is actually equivalent to this 4 bar. Okay. Sometimes practically you may use something like this because of space constraints, for example. So, if you look at, so say I increase the length of link 4, okay, then the arc that I get will be flatter. Okay. But if I keep increasing it to infinity, then what I get is basically a prismatic pair. Okay. But even in some cases, say I need a really long radius of curvature, really large radius of curvature for the path of this point at the end of link 4, the pivoting point, I might use a form like this, because it gives me some advantages from a practical consideration. But when you look at the kinematics of it, you are essentially looking at what is on the left hand side. Okay. So, it makes analysis simpler when you are able to identify the 4 bar in something that appears more complex. It makes the analysis a lot easier. Okay. And essentially the slider crank or the prismatic pair, it is just a limiting case of the 4 bar. That is why we always talk about the 4 bar and the slider crank in the same breath. You know, we talk about them as together, because essentially one is a limiting case of the other when the rocker pivot is at infinity. This is even more useful when this kind of what we call kinematic equivalence, or where the two linkages are equivalent for the purposes of, say, calculating velocities and accelerations. This kinematic equivalence is very useful, especially when you use mechanisms that have higher pairs in them. So, you take for example this cam driving another follower that has this complex shape. Okay. So, in this case, if you look at the center of curvature of this, so you have cam 2 and cam 3, cam 2 is driving cam 3, say. So, if you look at the centers of curvature at the point of contact, say A is the center of curvature. So, P is the point of contact, and then B is the center of curvature of the other link at that particular instant. Okay. Now, the property of the center of curvature is such that, so if you draw the common normal at the point of contact will obviously pass through the centers of curvature. The centers of curvature do not change for 3 infinitesimal positions. Okay, that is a property of the center of curvature. And so, using that we can say that the velocities and accelerations of this mechanism will be equivalent. So, if I replace it with a link connecting the two along the common normal, connecting the two centers of curvature, then I get this 4 bar. So, at this particular instant, the relationship between 2 and 3 is the same as the relationship between 2 and 3 in this 4 bar. important point to remember is that it is at that particular instant, because one of the things that you can do with a cam follower system is you can constantly change the radius of curvature between the two connected bodies, right. So, at a different instant you will have a different link AB connecting the two. Okay. So, you can use that to analyze. So, analyzing the 4 bar is a lot easier than analyzing the velocities and accelerations for a linkage with these higher pairs, for a mechanism with higher pairs. So, this is a way to represent a linkage with higher pairs with an equivalent 4 bar that is valid at that particular instant, and then use that for analysis. The other side of the picture is what makes the cam follower system so versatile is that it is essentially a series of changing 4 bars. So, you can look at a cam for, so you have much more flexibility in, with a 4 bar once you have a set of links, what motion you get is what you get, right. With a cam follower system where the input and the output members are directly in contact, you can see that it is essentially a series of changing 4 bars, and therefore, you get a lot of flexibility in designing the input output motions. But cams of course have other problems, especially with respect to wear, maintaining contact between the links, etc. So, in some linkages typically are preferred, but of course again it depends on the application. That is the caveat everywhere, it always depends on the application. Here is another cam follower system where you can see that in this case the center of curvature for this link 2 is here and for link 3 is here. So, you get a crossed 4 bar linkage that represents the system at that particular instant. Okay. So, you can use this for velocities and accelerations, not for higher derivatives. This kind of an equivalent linkage can be used to compute instantaneous velocities and accelerations. Here are some more examples similar to what I just showed you. Essentially here, if this is A naught A, if this is B, then this will be B naught. So, my 4 bar will be A naught A, A B, B naught. So, this will be my equivalent 4 bar. Similarly, here if this is this will be B naught, this is the center of curvature of that. So, this will be my, so if I call this 1, 2, 3, 4 here, this is 4 dash, 1, 2, 3, 4 dash is my equivalent 4 bar. Here I have 1, 2, say the block is 3 and this is 4. Now, this is my 3 dash, this is my 4 dash. The equivalent 4 bar would be 1, 2, 3 dash, 4 dash. Okay. So, the input output relationship will be the same between 2 and 4 dash, and here between again 2 and 4 dash at that particular instant. In a few cases, so here is a cam follower system but it uses a circular cam, okay, which is just pivoted with an offset, right. So, you have in this case, because the centers of curvature do not change throughout the motion, this can be represented by an invariant equivalent linkage. So, it is the same 4 bar that I can use to analyze the motion over the entire range. Okay. So, the instantaneous 4 bar is the same as the 4 bar at every instant, okay, which makes life a lot simpler. Analyzing this is a lot easier than analyzing this. Okay. So, this is the use of equivalent linkages. One more. So, here I have a cam with a roller follower. What is this curve called? Pitch curve, yes. So, you use the pitch curve, so I have, so what is the nature of the motion? I have, this is the center of curvature of the pitch curve, and the motion that I have is, what would I do? How does the follower move? Sorry, this is not fixed. I have 1, 2, and let us just call this 4. What is the nature of motion of 4? 4 is essentially a block. It is moving with respect to 1, okay, and the motion of this would be equivalent to this would be 2. So, this would be the kinematically equivalent system with just lower pairs. We saw earlier for the pin in slot, okay. You separate the higher pair motion into a lower pair, 2 lower pairs basically. So, I will give you some exercises. Yes? It is only instantaneous because the pitch curve keeps changing. So, the center of curvature will keep changing. So, this link 2 dash will keep changing, so will 3 dash. Okay.
Like then, the kinematic equivalence we only called for when it was at all times.
That was only in this special case. In this special case, because the radius of curvature of this cam does not change, A is always the center, it is a circular cam. So, here you can represent, it is a very special case where you can represent by a 4 bar that does not change. In most cases, it is only applicable at a particular instant. Next instant everything changes. Okay. So, with this kind of thing it may be difficult to do, unless you have the equation of the cam surface, that it's a little tricky to do the analysis, but if you are interested say in only certain positions, you are interested in the velocities and accelerations, then for those positions you can represent them by an equivalent linkage and then do the analysis. This one you have A, this is B, B naught. So, my equivalent linkage is this. okay, lot easier to analyze. So, this is the concept of kinematic equivalence. One more, you have time. Okay. So, this thing is moving along this portion here. In cams, you know, you can have, sometimes you can have portions that are straight lines, right. So, the radius of curvature is infinite, the center of curvature is at infinity. In this case, you can represent this by, so this motion is up and down. So, I can have a link with a slot, okay, and instead of a roller I would represent it, sorry, by a block, and then attach this link to it. Okay. So, this would be my 2 dash. So, this is welded here. If I draw this separately, be something like because the follower is moving in line with this. So, it is essentially like this link is pivoted